Observe a rigid robotic arm executing a precision weld and a wheeled rover accelerating across a factory floor. Physically, these machines operate through entirely different mechanical architectures. Attempting to control them by dictating direct position coordinates requires solving dense, nonlinear geometric equations. For high-frequency control loops, the iterative numerical solvers needed to find these coordinates introduce a significant computational burden. Advanced robotics bypasses this bottleneck by operating at the velocity level. Rather than asking where the robot is, the controller determines exactly how fast each internal actuator must rotate to produce the desired external speed. The relationship between task space velocities, x dot, and internal joint velocities, q dot, is governed by the Jacobian matrix. It provides a linear approximation of kinetics, functioning as the geometric blueprint dictating real-time capabilities of both manipulators and mobile platforms. Extracting the math behind this matrix reveals the central logic engineers use to command intelligent, coordinated movement in nearly any mechanical architecture. Consider a planar robotic arm with 2 degrees of freedom. To map its velocity profile, we calculate the first-order partial derivatives of its forward kinematics equations. Position formulas differentiate into a 2x2 matrix mapping the arm's configuration. Column 1 calculates the velocity vector tangent to the base radius when the base rotates. Column 2 maps the elbow's velocity vector. The total end-effector trajectory is the linear combination of these vectors. The values in this 2x2 grid rewrite themselves with every fractional degree of movement. It maps the physical envelope of the machine continuously. To drive the end effector along a precise target path, the control logic runs in reverse. It takes the desired task space velocity and mathematically inverts the Jacobian to calculate the required joint inputs. This algebraic inversion relies entirely on the determinant of the matrix. If the arm extends until both links form a perfectly straight line, that determinant drops exactly to 0. Here we see the manipulability ellipsoid, a geometric plot of achievable velocities. At full extension, the ellipse crushes into a flat one-dimensional line, losing an axis of mobility. If a controller commands outward motion, the inverse equation divides by 0, demanding an infinitely fast joint velocity. Real hardware saturates and fails under infinite demands. To intercept this mathematical collapse, engineers implement a regularization technique known as damped least squares. By injecting an artificial damping factor into the inverse equation, the controller suppresses the mathematical explosion. The system intentionally sacrifices strict adherence to the requested path to keep the physical joint speeds bounded and safe. Singularities force a hard engineering compromise. The algorithm must abandon perfect spatial accuracy to prevent the mechanical hardware from tearing itself apart. The Jacobian matrix also governs the forces a robot exerts against its environment. Through virtual work, the Jacobian's transpose maps external forces into equivalent motor torques. This creates a speed-strength trade-off. At the extended singularity, the arm cannot generate outward speed, but it can absorb enormous structural compression along its links with almost 0 holding torque. The matrix functions as a dynamic, programmable mechanical lever. The machine trades pure speed for brute strength based entirely on the angles of its current posture. Applying velocity-level logic to a wheeled system requires mapping independent wheel speeds to forward momentum and rotational heading. The unicycle model uses an ICE-eta matrix to link body frame velocities to global coordinates. This 3x2 matrix connects 2 wheel inputs to 3 planar dimensions. Forward and rotational vectors never align parallel, avoiding singularities. The trade-off is a permanent non-holonomic constraint. It cannot sidestep. While an arm temporarily loses degrees of freedom by twisting into a poor posture, a rover operates with a perpetual geometric blind spot, requiring calculated multi-step maneuvers to adjust its lateral position. A rigid arm in a resolved rate control loop and a rover executing a go-to-goal trajectory appear distinct, but their architectures are identical. Both systems follow the same logic: define a target, invert the kinematic matrix, and execute precise commands to the physical actuators. Fusing these 2 physical models together yields a mobile manipulator, a multi-axis robotic arm anchored to an autonomous wheeled rover base. This combination results in a platform possessing significantly more internal motors than physical task dimensions. To calculate exact control instructions for this rectangular matrix, the system requires the Moore-Penrose pseudo-inverse. This specific mathematical operation isolates redundant mechanical movement into a null space. The platform can seamlessly contort its posture or evade sudden obstacles without altering the precise path of its end-effector. Mastering the Jacobian provides the mathematical framework required to coordinate these multi-layered systems, turning complex hardware into a single controllable unit.